Sorry. The Chem 1B, which is kind of this olive green color, those are soft cover, soft bound books. So those are the half text. Or you can buy the full text. If you want the full text so you can see the Chem 1A, then buy the white hard cover book. We're currently on the 11th edition, which is the most recent, 2017. In fact, it just came out. So this is what. There's the lab manual. The lab manual is a bit tricky because the lab manual is just a photocopied manual. It's going to be all loose leaf like this, and they just have it wrapped in plastic. But it's not on the shelf. What you have to do is you have to go to the, what they call the book buyer's office. If you go in the bookstore, it's on the left-hand side near the back, and you'll see some windows there. You have to go to one, the middle one, I think it is, and you have to ask them for the Catalyst book here. And so they have some of these printed out. They're kind of expensive, $20 for a photocopied loosely. All right. This, though, I have to apologize. There was a mistake at the bookstore that was made this semester. And that is, they gave a tag for my class with the research notebook. The research notebook has duplicate pages, spiral bound, $20 notebook. You don't need that. If you bought one already and you're taking organic, then you can use that for organic chemistry. That's the one they require there. But for this class, you can just buy one of those simple, composition notebooks that you get at the Target or Office Depot or Staples. In fact, I was just at Staples. This is not a plug for Staples, but it was on sale at Staples, $1 each, for the composition notebook, quad ruled, which is the graph paper roll with sewn. Sewn binding just means it's going to be taped. It has no tear out pages. In the lab notebook, you don't want any tear out pages, or you don't want to be able to remove pages without. We'll talk more about this later. We aren't going to need this for a little bit until next week or so. Safety goggles. Usually the safety goggles that you have in Chem 1A will work fine here. I do have to check them though if you brought them from a different school, because different schools have different requirements. A scientific calculator. The scientific calculator, what you want is you don't, I mean, if you already have one, that's fine. You can use it, but what you might want to get is the $15 calculator rather than the $10 calculator. The $15 calculator has a little bit more functions to make life easier in Chem 1B. And what you're looking for in the $15 calculator is you're looking for one that has an equation solver. Not a programmable calculator, because programmable calculators aren't allowed. So if you have like a TI, whatever, 92 or 80, whatever, those are actually not accepted for tests, general chem. And they aren't accepted for, I think, for standardized tests as well. But an example of a scientific calculator that has an equation solver would be something like this is the calculator I've been using, Casio FX115ES, that one. So this one's available at Target, Walmart, all those places. I've bought a bunch of these, and those are pretty good calculators. And so this one has a equation solver that solves quadratic equations. Actually, this one solves up to third order equations, which is pretty useful. And so scientific calculator. Fine point permanent marker, like a Sharpie pen, is pretty handy to have. At UCLA, they require this now. I think at all UCs, they require everybody to wear a lab coat. Oh, we have lab coats available at the bookstore. They aren't that expensive, I think. Or you can buy them on Amazon as well. I bought my last lab coat on Amazon. I think it was a $16 lab coat. You know, some labs require cotton lab coats for fire resistance. We have two different. We have at the bookstore here the cotton and just the cheaper fiber one, and I think the cost is not so much. Usually, when you do lab, you know, sometimes you get little splashes on you, and you don't notice it until you wash your clothes, and then you see you have lots of holes in your clothing. So you shouldn't wear very nice clothes to lab or very expensive clothes. And also be aware of the material. You don't want anything that can catch on fire easily. Gloves are always handy. These are required now at UCLA. I prefer nitrile. Nitrile gloves breathe a little easier, and so your hands don't get all sweaty like in latex gloves. And nitrile gloves are more resistant to most of the chemicals we use. They have much better chemical resistance. Not all gloves are totally impermeable to chemicals, though. You know, nitrile gloves, with certain chemicals, 5 minutes you have to throw them away because they've already been saturated with like sponges. Once they're saturated, the chemicals flow through. But for aqueous solutions, they'll last all day. In fact, maybe more than one day if you reuse them. For organics, organic liquids like alcohol, ethers, that kind of stuff, maybe acids, etc. Okay, so any questions on the course materials? All of the assignments are required. Yeah. If you do miss an assignment, it depends on what type of assignment. Lab, we'll try to do a makeup lab. This is a morning section, so there's an afternoon section. If there's room there, you can make it up there in the afternoon section. If something happens. Exams are more tricky if you miss an exam. If you miss it and you can make it to the afternoon, that would be good. But if you miss it, then makeup exams are subject to potential penalties depending on the circumstances because of the extra time. It depends, though. So hopefully you don't miss any. That's the best. The grades, we're going to have exams and quizzes, which are going to total about 500. These are just approximate points here. The quizzes are going to be between 1 and 5 points each. Exams, 50 to 65 points. We're going to have a lot of exams, so I'm going to break it up into not just one midterm or two midterms, but lots. We're going to have homework. Paper homework, I'm not sure about that. I might just do Mastering Chem homework. Does everybody have a Mastering Chem account? Who doesn't have a Mastering Chem? I'll think about this. I don't know what the cost on Mastering Chem is right now, but and so this paper might be online and paper homework. There's a late penalty on the homework, though. The late penalty is half. And that is the homeworks are going to be due on the exam day. So if we have an exam, all the homework that's pertinent to that exam will be due on that day. You can still turn it in all the way up to the end of the semester for credit. So it's 50% is better than 0. Labs, I'm pretty flexible with the due date, and so it's rare that somebody gets hit with a late penalty on the lab. So I think I give plenty of time for labs. Anyway, we have experiments. 15 points per experiment or so, except for some, like this qual means qualitative analysis is 35 points. This is a very long lab. Synthesis, I'm not sure if I'm going to have all 3 of these as 30 pointers. We might just do 2 as 30 and 1 as 15. We'll see how things go or progress. And then the final exam. Final exam is going to be about 200 points, which is 20% of the grade. And it's going to be comprehensive, so we'll cover everything from the beginning to the end. The grade distribution here is going to be 100 to 88 is A, and then 88 to 78. This is kind of my curve here. 78 to 65 in C. Yeah, when this converted to PDF, it didn't convert. I didn't notice this, but we'll see this. Important note regarding grades: if you fail the lab, you know, this course is different because at UC the lab is separate from the lecture. The lab is 1 unit, the lecture is like 3 units, and so you could do well in lecture, but fail lab, you'll fail 1 unit. But here, you know. Here, if you fail lab, you fail all 5 units, which is very unpleasant. You know, there's some people who don't like lab, who just like the lecture stuff. And it happens. I don't know why it happens, but some people don't show up for lab. They end up doing well on the tests, but I think they're thinking UC mentality or something. But they end up failing the course, even though they have a passing grade, which is unfortunate. And so just be aware of that. Laboratory attendance is mandatory. You know, if you start missing labs, I'm going to notice that. If you start missing lectures, it's okay. I'm not going to deduct points for missing lectures, but if you miss lab, that's much more serious. Cheating is, this is what's supposed to say academic honesty here is expected. That just goes, there are different philosophies on cheating. When I was at the UC, because as a teaching assistant, let's say at UC, some professors that I worked with, they didn't care. You know, if somebody cheated, they said, eventually the class gets smaller. As you go up, the classes get smaller and smaller. Pretty soon you're in a class, there's only 10 people in the class, and it's pretty obvious to the professor who doesn't have the foundation. They don't belong in the class, and it's easy. And as you progress, the people who had to rely on cheating are going to be the attrition, the dropout rate is pretty high. I think when I went to UCLA, they were even saying for transfer students the attrition rate is high, but the transfer rate students had a much higher success rate than the people who started off as freshmen at the UC. They were saying that like half of the incoming freshmen don't finish, but the transfers had a much better percentage. But that was so many years ago. I don't know what it is now. Maybe it's quite a bit different. If there are any special needs, talk to me, or there's student services that can help. I think I got some papers. But any changes, I'll usually post these on Piazza, or actually both, lecture and Piazza. The problem with saying it in lecture is that, in lecture, lots of studies have been done, I think, with lecture, and the amount of information that people retain from lecture varies dramatically. There's some people who get nothing, like 10% of what the material that's presented in lecture, they remember. There are other people who remember a very high percentage. And so I'll try to do both here. All right, finally, the definition of chemistry. What do chemists do? They study, the properties of matter. When we look at the properties of matter, this says properties and reactions. Chemists don't consider properties and reactions separate. Chemists consider properties, both physical and chemical properties, to be under the category property. And so the physical properties are just your boiling point, etc. But the chemical properties are the chemical reactions. These are the chemical reactions. And so this is what? This is American Heritage Dictionary definition of chemistry is not exactly the chemist's definition of chemistry. The chemist's definition of chemistry was we eliminate the reactions. It would be the composition, structure, and properties of matter. That's what we're studying. And so we want to understand the properties, both physical and chemical properties of matter. Well, one thing you can do is they have books. They have books of properties of chemicals. You know, books called the. Actually, I should have grabbed one before coming in. But I can just show you what it looks like. Nice. Well, this book is I don't know how many pages. It's about this thick. This book is. And it's just filled with properties of matter. CRC handbook. This is very. This is more geared towards inorganic and somewhat organic. And then there's another one. There's two books I used to use quite a lot: the CRC and the Merck Index. Oh, the Wikipedia. Ooh. The Merck Index has 10,000 monographs or 10,000 compounds in there. It's not comprehensive by any means, but the Merck Index is also very thick. I think over 1,000 pages. Merck Index focuses on biomolecules and organic molecules. Organic, as you would call them from chapter 3, or carbon based. But obviously, it's too much to memorize. You know, and these are just too many. There's an encyclopedia of many volumes with properties in there. Do you memorize all that? Some people do. They'll go through and memorize, and it's good to memorize a lot of properties so you know. For example, you know, if you didn't know chlorine, is chlorine a gas, liquid, or solid? It's a gas. How did you know that? How did you know that? You memorized it, right? That's a lot easier than trying to do some theoretical calculation, like in using quantum mechanics and Schrodinger equation to figure out is chlorine a gas, liquid, or solid, although, you know, you could. Well, the same thing here. You know, you could go through, like if you're interested in certain classic compounds, you probably want to go through and memorize a whole bunch of those so that you get a better understanding of that. But it's too much to memorize. We don't want to have to memorize. We want to keep the memorization to minimum. And therefore, we want to relate properties to what else? You know, if we understand this more from a theoretical kind of standpoint, or, you know, if we can get more insight into it, then that would be quite useful. So what we try to do is we try to relate properties to the composition. Obviously, the composition is going to give different properties. Like, for example, diamond. Diamond has certain properties. It's extremely hard, consists of the element carbon, high melting point, etc. Those are properties. Those are physical properties. What kind of chemical properties does diamond have? Is density a chemical property? Or a physical property? It's physical. Tell me some chemical properties of diamond. Yeah, that's the answer I expected. You probably can't tell me any chemical properties because you focus entirely on physical properties, right? This bias has happened, you know, ever since I was a student. You know, but when I was at UCLA, I had to take an oral examination. once. It was only one oral exam, and it was unusual for undergrad oral exam. But everybody in this class took an oral exam. Basically. During the oral exam, I got a question. What are the chemical properties of phosphate? And then I was thinking, chemical properties of phosphate. I never thought of it. Just like probably you, I never really thought of it. What are the chemical properties of phosphate? And so I said something like, and there are three professors there, and just me standing here. And like each second was like, of silence was like, everything was slow motion thinking. But it was bad because, everything was going okay up to that point. And then this question hit me, and then I was thinking, well, it's in detergents, like trisodium phosphates in detergent. I saw that later. It must clean stuff. But I didn't really have a good answer, so I started thinking, okay, what does phosphate react with? React with acid. And so you start thinking, in terms of chemical properties, the way people start thinking about these is they think about mixing individual chemicals with that. What chemical individual? Does sodium hydroxide react? What about potassium hydroxide? What about lithium hydroxide? Well, if those don't, what about this? What about that? And so I was kind of at a loss because when I learned about chemical reactions, I learned that there were many, many, many different types of chemical reactions. So many that I didn't even bother because it was just too many. Types of chemical reactions that, who knows, just get a test tube, mix it together and see what happens, right? But anyway, it turned out okay. I kind of just tried to wing some kind of answer together, but it wasn't very good. I didn't feel good about my answer, but that was only one question of many, though, so it wasn't fatal. Anyway, when we think about properties, we got to think about, the structure as well, because, for example, diamond is very different from graphite. Diamond and graphite have the exact same composition, but they have totally different properties. And the totally different properties are because of the structure. And so what we want to do is we want to start thinking about this. In terms of properties, how can we relate these things to composition and structure that we can come up with something more systematic. Phosphate has this kind of structure. There are lots of things about phosphate I could say now, but that I remember that experience quite well. And then I've always thought about chemical properties, And so if I were to ask you, how many different types of chemical reactions are there in nature? How many different types of chemical reactions? At least just on Earth, if you think about just the reactions going on in your body, how many different chemical reactions are occurring in your body right now, or just around you? A lot, right? And if you think about the types, how many different types? Are there an infinite number of types? If they're an infinite, why bother? It's too much to memorize. Or are there a limited number of types? Or is there only one type of reaction? How many types? And so if you took Chem 4 here, there are a lot of types. I think they had, how many different types of reactions in Chem 4? It was crazy. Metal oxide plus acid. Metal oxide plus water. Non-metal oxide plus water. Do any of those ring a bell? Probably, maybe not. Maybe you said, oh, that's too many. Forget it. But it turns out it's not that, not that complicated. There are basically only three basic types of chemical reactions that we'll discuss in this. And so, now I would say, okay. For phosphate, it's easy. Phosphate's a base. We can react with acids. It's an acid-base type reaction. That's one type of reaction. Phosphate is a 3- ion. 3- ions can be attracted to cations. -3, anything positive is going to be strongly attracted to it. Although +1, maybe not So +2 for sure. So it's going to precipitate out with +2 cations like calcium, strontium, barium, +3 cations. No problem. In other words, you learn in the solubility rules that phosphates are all insoluble except for group 1 and ammonium. Right? That type of reaction we call a metathesis reaction, just ions that like each other. And then as far as redox, phosphate should be a mild oxidizing agent. We're going to cover that this week, so that's where we're headed. But that's what we want. I mean, that's chemistry. Chemistry deals with the properties. So I switched this around. The overhead projector is so bad in our lecture. I'm not sure what we're going to do right now, but this week we're covering reactions today and tomorrow, and then on Thursday we're going to start chapter 13. This reaction stuff is a composite. There's not a chapter in the book. It's composite material from chapter 3, chapter 5, and another chapter. I'll tell you what chapter it is. Chapter 18. Or 19. Then Monday's a holiday. And we're going to continue chapter 13 here. Chapter 13, this is why I want you to review Thermodynamics Part 1. Chapter 13 is Thermodynamics Part 2. So you have to know all that stuff. For example, what's the definition of enthalpy? Or maybe not the definition, just tell me what enthalpy is. What is enthalpy? Put it down in simple, huh? Enthalpy is the total kinetic and potential. Close, very close. We would call the total kinetic and potential energy the internal energy of the system, not the enthalpy. And the enthalpy is different than the internal energy. And so what is the enthalpy, and well, that's important. How does it differ from the internal energy? Well, it's a change in heat. So if something like let's do a chemical reaction, really quick. If we do a chemical reaction, methane and oxygen, is this a stable mixture? These are G's for gases. Is that a stable mixture or unstable mixture? Methane and oxygen. Stable or unstable? So if I fill this room up with methane, are you comfortable or uncomfortable? You'd be uncomfortable because it's an unstable mixture. We call that a high energy mixture, right? This is a little bit more review for Chem 1A because I want you to know this. Okay, what is the total energy of this? Oh, if I leak methane in the room, let's say this is at room temperature. Do you know what room temperature is officially? Room temperature varies, of course, depending on what we have the AC set at, right? But what do chemists call room temperature? Not 20. 20 is a little bit cold. Although 20 would be comfortable. I'd much rather have 20-degree room temperature than this room temperature. But the standard room temperature is taken as, I heard it, 25, right, Paul? 25 degrees C or 298 Kelvins, your standard room temperature, which is too warm for me, but that's what people take it at. And so let's say this is at 25 degrees C. Does this have a high enthalpy? Does this have a high heat? You know, if enthalpy is like heat loss or heat gain, right? Heat loss or heat gain, then let's do this reaction. CO2 and water, is that a more stable mixture or a less stable mixture? CO2 and water. It's a more stable mixture. CO2 gas and H2O liquid. I'm going to have two of these to balance it. So what I'm going to do is this. We're going to take this unstable mixture and create a more stable mixture by just combusting it. Right? And so this is methane and oxygen, and it's going to form CO2 and water. That flame is very hot, right? But when I stop this, what's going to happen to the CO2 and water? Is it going to stay hot forever? No, eventually it's going to cool back down to room temperature. And so now we're at 25 degrees C. So we start out at 25 degrees C, we end at 25 degrees C. So what is enthalpy? Enthalpy is heat lost. Was heat lost? It depends on, you could say heat lost, but usually when people say heat lost, you have a bucket of hot coffee and it cools back down to room temperature and heat lost. The coffee is now cold, right? That's normally what people think of in terms of heat loss and heat gain. So maybe we shouldn't use that exact terminology for this. What should we use? Yeah, maybe heat was evolved. Heat was evolved in this reaction, that's for sure, because what happens is this. You guys recall from kinetic molecular theory that kinetic energy and temperature are actually, there's one more thing you have to review. The one more thing you have to review is this. You have to review gases. I was going to do the review just yesterday, but we're going to bleed into a little bit today because we need to talk about air. Air is a mixture of what? Yeah. So the two biggest components are nitrogen and oxygen. Let's say I have 1.0 liters of air. If I have 1.0 liters of air, how many liters of nitrogen do I have? Okay, let me tell you, air is about 80% nitrogen, 20% oxygen. If I have 1 liter of air, let's say this is 1 liter of air. What did you do in Chem 1A, bar or atmosphere? Atmospheres? Did anybody do bar? All right, let's say we have 1 liter of air and 1 atmosphere. At 1 atmosphere. And so I have 1 liter of air, 1 atmosphere. Well, we got 1 liter of air, about 1 atmosphere in this room. And so if I take 1 liter of this air in this room, how many liters of nitrogen are in that 1 liter? 0.8 liters? And so if I have 0.8 liters of nitrogen, what is the pressure of just the nitrogen alone? Would it be 0.8? So I'd have 0.8 liters of nitrogen at 0.8 atmospheres. Is that true or is that false? 0.8 liters of, that's false. It would be 0.8 liters of nitrogen at 1 atmosphere. And then I would have how many liters of oxygen? 0.2 liters of oxygen at 1 atmosphere. And what's the total pressure? P total. P total would be 2 atmospheres? No, P total will be 1 atmosphere. But doesn't this violate Dalton's law? Wouldn't Dalton's law say 1 atmosphere plus 1 atmosphere gives you 2 atmospheres? Or it doesn't violate Dalton's law? Does this violate Dalton's law? True or false? This is a violation of Dalton's law. 1 atmosphere plus 1 atmosphere gives us 1 atmosphere. Violation of Dalton's law? Or not? But no, this is not a violation of Dalton's law because Dalton's law is not valid for this case. This is a case of what we call Avogadro's law. If we wanted Dalton's law, we can't think of it like this. If we wanted Dalton's law to be true, if I have 1 liter of air, how many liters of nitrogen do I have? Avogadro's law says the volumes are additive. So 0.8 liters plus 0.2 liters gives me 1.0 liters. If I wanted Dalton's law to work, this exact same mixture, right? But there are 2 ways of visualizing air in this room. One way is by Avogadro's. If we're visualizing via Avogadro's, then we keep the pressure constant, and therefore Dalton's law doesn't apply here. Or we visualize this using Dalton's. The problem with our book is they just do Dalton's, and so this is why I'm reviewing this a little bit, because everybody thinks in terms of Dalton's rather than Avogadro's. For thermodynamics, we have to think in terms of Avogadro's, not Dalton's, for thermodynamics. Now, and this from Thermodynamics Part 1. I don't know if it's so clear in that chapter. But for Dalton's, how many liters of nitrogen do I have? If I'm visualizing this air as being a Dalton's mixture versus an Avogadro's, how many liters of nitrogen do I have? 1. 1's correct. We have 1.0 liters of nitrogen at what pressure? If I'm just looking at the collisions of the nitrogen, then 80% of the collisions are from nitrogen. Therefore, 80% of the pressure will be from nitrogen. And so it's going to be 0.8 atmospheres. How many liters of oxygen do I have? 1 liter. I have 1 liter of oxygen at 0.2 atmospheres. So I take this exact same box and I just look at the oxygen collisions. The oxygen collisions are going to be 20% of the collisions. And so that's only going to give me 0.2 atmospheres. And so in this case, with the Dalton's type, we see that the pressures are additive. 0.8 atmospheres plus 0.2 atmospheres gives us 1.0 atmospheres. And then 1 liter plus 1 liter gives me, 1 liter plus 1 liter gives me, no, 1 liter. Okay, so in Dalton's, the volume is constant. In Avogadro's, the pressure is constant. It doesn't change. Okay? And in thermodynamics, we think in terms of this, because in thermodynamics, we're looking at chemical mixtures, reactions, right? In a chemical reaction, you're mixing methane gas plus oxygen gas. And so the easiest way of thinking about this is if I take, let's say if I take 1 liter of methane, how many liters of oxygen will I need? If I have 1 liter of methane, I'm going to need 2 liters of oxygen. That is Avogadro's. That's not Dalton's. Dalton's would be, if I had 1 atmosphere of methane, I'd need 2 atmospheres of O2. We don't think in that way. And so even the chapter, whatever, the gas chapter was Dalton's bias, really what you need is an Avogadro's bias for thermodynamics. So you got to go back. If this stuff is not so clear, a little bit fuzzy, then you got to go back and review this. Okay? Also, you got to go back into the gas chapter and review this. These 2 mixtures have the exact same length. These 2 mixtures have the exact same temperature, yes. They have the exact same mass, yes, conservation of mass, that's good. They have the exact same pressures, yes, because all these are going to be Avogadro's. So we have 1 atmosphere of methane, 1 atmosphere of O2. Right? 1 atmosphere of methane plus 1 atmosphere of O2. This is going to be 1 liter, that's going to be 2 liters. Or this is going to be 10 liters, that's going to be 20 liters, right? And the same thing down here, except water is a liquid, not a gas. Water is a liquid at room temperature. That's good. They are going to have the exact same pressure, 1 atmosphere. Usually 1 atmosphere is the pressure we use, or 1 bar is the pressure we use. In fact, we do this. You guys remember this? What does this mean? That little superscript.
Degrees.
Not degrees. We would call it delta H not? What does that little superscript 0 mean? Paul? Save me here. Kelly? It's easy to forget, you know. The summer, it's easy to forget. Oh, go ahead. Initial? I'm sorry?
I said STP.
STP is close, but STP is standard temperature and pressure. But it's not STP, but it's close.
Constant pressure.
Well, did you know delta H? This alone tells me it's constant pressure because I know the definition of H. Do you know I asked you the definition of H already. In the definition of H is constant. H has to be a constant pressure. Otherwise, H is not valid. This is why Avogadro is important. This is why back in chapter 7, you know, you should have been thinking in terms of Avogadros, not Daltons, because H already contains that. It's got to be. If it's not at constant pressure, you can't use H. It's not valid anymore. But anyway, you should go back and look at what H is. And the best thing is, you know, the best thing is this. First, you memorize the book's definition, but then you start, after you memorize the book's definition, then you start putting it in your own words. Because if you just try to regurgitate the book's definition, it doesn't, it's hard to remember, you know, and it's easy to forget. And so if you make your own definition of H, it's in your own words, it's really difficult to forget that. You know, it's going to be ingrained because you made it. You know, it's your definition of what H is. You know? And it makes it just much more meaningful. But anyway, thermodynamics, let me just tell you. When I looked at the book, because thermodynamics used to be chapter 19. And then in the 11th edition, they moved it to chapter 13. And then I had reservations. I was thinking maybe I'm going to push it back. Or maybe I'll just leave it. Because thermodynamics is one of the toughest things conceptually. You know, anybody could do a delta H calculation. The calculations are so easy. It's like ideal gas, you know? You do the calculations seem very easy. You got an equation, you just plug in the numbers, right? The problem is nobody knows what it means, you know? Nobody really knows that. It's like in ideal gas. If you use the ideal gas equation for helium, that's great. But what if you use this for a different gas? What if you use it for CO2? Would you have still as much confidence in the answer as you would with helium? No, you would say the answer you get for CO2 will be off a little bit because CO2 is going to deviate from ideal behavior more significantly. Right? But anybody can plug in the numbers because if the numbers are exactly the same, we'll get the same answer, right? The problem is knowing, you know, the meaning of the numbers. The number that we get from helium, we can have a lot of confidence in because helium is very ideal, you know, under normal conditions. CO2 is not. The same thing. If we do a calculation of 1 atmosphere versus 100 atmospheres, you know, we just plug in the numbers, it's very simple, but at 100 atmospheres, do things behave so ideally? No. And so we're going to expect greater deviations or greater errors in our answer at 100 atmospheres, right? So this is the thing that that's so important, and it's understanding what the numbers mean here. It's understanding what the symbols mean because you know you could do it. Delta H is equal to the sum of the delta H's formation of the products minus the sum of the delta H's formation of the reactants. You look it up in the book, plug the numbers in, punch it out in your calculator, and you're done. But what did you just calculate? What exactly is that number? That's the tough thing. And so you can get by, you know, you can get by, but eventually you can't get by. You know, eventually you have to know it. And by the time a lot of people have to know it is then they have to do a lot of review, because this is what happened to me. When I transferred to UCLA, the first class I took at UCLA was thermodynamics. And I studied, because when I went to orientation at UCLA, they told me that my GPA is going to drop by 1 unit. I thought, okay. Most people, in fact, most everybody's GPA drops by 1 grade. And so I thought, well, it's not going to happen to me, because I'm going to study. I'm just going to focus on studying. Although, I don't want to make any excuses, but I also worked in the cafeteria. And right before the final exams, 5 people quit. And so they had to assign me extra shifts. But, I was okay with that because I had studied. I had really studied hard for this course, but I wasn't doing it. The first test I got back, I think I got like a D. I couldn't believe it. All I did was study. Every moment of time I had was devoted to studying, and how could I get a D on that test? I think that was what it was. Maybe it was an F. I don't remember so well. It was just bad. I just remember it was very bad. And so, anyway, why? I could do these calculations easily. I had no idea what delta H meant. Somebody asked me, define delta H? Define enthalpy? I can do the calculation. Give me the numbers. Let me plug it into the equation. I can do that. But, I couldn't do beyond that. That was the problem. And so what I had to do is I had to go back and, that was for the midterm. Then there's 1 midterm and 1 final. And so I had to do very well in the final, otherwise I wasn't going to pass the class. And so I had to go back and through and review everything. And so I ended up buying the general chemistry book they use at UCLA, which talked about thermo in much more detail than my general chemistry book. And I went back and I reviewed all the basics and tried to learn all that stuff. Whereas the guy next to me had no problem. The guy next to me didn't seem to work that hard, and he was doing very well in the class. And he was a transfer student as well, and I got to know him actually pretty well. And so we started. I started asking him about his study habits and this kind of stuff and that kind of stuff. And so I learned quite a few tips from him about how to study. And so anyway, to make a long story short, I finally figured out, the way I'm studying, the way I'm thinking about the material is wrong. The way I've been doing things before isn't the way I need to be doing things there now. So I totally revamped the way I studied when I was a student at UCLA. But you have an opportunity now, because it's not too late. If you didn't learn this stuff in last semester, then, or at least maybe you learned it and forgot it, you still have time. Because a lot of people have to take thermodynamics. They have thermodynamics for biologists because energy is very important in biology, biological systems. They have thermodynamics for engineers. They have thermodynamics. In fact, there's a debate. I was looking at. There's always a debate between what's harder, thermodynamics or organic chemistry. And so I searched the internet, and you could search this too if you want to read about it. There's something like the Harvard students board, and they have this ongoing debate about what's harder, thermodynamics or organic. But thermodynamics is known as a leader class. In fact, at UCLA they have a bumper stickers that you can buy. It says I passed Chem, which is thermodynamics. I didn't buy one. But anyway, getting back to this, when you review this, you got to be thinking about that kind of stuff here. And so here, just as far as this goes, and I'm going to stop there. So, what's the difference here? The difference is in terms of, well, what's the same here? Temperature's the same, pressure's the same. The pressure's the same if we don't think in terms of Daltons. What else is the same? The volume is not the same. Volume. Did you guys memorize 22 point? Did you guys have to memorize the molar volume of gas? 22.4. Did you guys memorize that at STP? Okay. Uh-huh.
They both have the same internal energy.
They don't have the same internal energy. Internal energy is actually different.
But they're the same temperature, the same mass. Right?
It's not the internal energy that's the same. It's a component of the internal energy that's the same. Well, think about it for a minute and then see. You know, what does internal energy consist of? You had it earlier. You told me what internal energy consists of. So think of it in those terms. But getting back to the molar volume of the gas, I had to memorize that in Chem 4. When I was taking Intro Chem, and in fact, I had it memorized before Chem 4 because in high school, I memorized it, I think. In high school, I memorized 22.4 liters per mole of gas. That is so burned in my memory, I cannot forget it. I've been trying to forget it because it turned out to be completely worthless. I memorized it, and I had it continually memorized, and you know how many times I've used it? 0. I've used that 0 times. Totally worthless. The reason it's totally worthless is what is STP? STP is standard temperature. What is standard temperature? 0 Celsius. How many chemical reactions do you do at 0 degrees Celsius? When I worked in the lab, I didn't walk into a freezer box set at 0 degrees Celsius to work on my chemicals, right? That's why it's totally worthless, because nobody that I knew worked in a 0 degree C laboratory. Most people work in a room temperature laboratory. Unfortunately, this is a little warm for me, but room temperature is 25 degrees C. So what's a much more valuable number is the molar volume of the gas at 25 degrees C, which I do have memorized. The molar volume of the gas at 25 degrees C is 24.45 liters. 24.45 liters are roughly 25 liters. So I look at the volume here. This is 25 liters. If that's 1 mole, this is 2 moles. That's going to be 50 liters. This is going to be 75 liters of gas. This is 25 liters, and then 2 moles of liquid water. 2 moles of liquid water weighs 36 grams. 36 grams is 36 milliliters. So this is going to be about 25 plus about 36 milliliters. 25 liters, so 25.04 liters, roughly. And so the volumes are totally different. Those volumes are very useful because in thermodynamics, like I said, these gas mixtures, we got to keep track of this because we got to do calculations. What type of calculations do you do? Well, if there's a volume change, there's going to be work involved. You guys remember work and heat? And so we got to know how much work was involved in this. In fact, who does the work? We go from 75 to 25 liters. Who's doing the work? The surroundings or the system? Who's doing the work? The surroundings. And so the system is going to gain energy from the surroundings doing work. And so in this case, this is what, when I see this, if this is in terms of internal energy, delta U, then I see that the surroundings is going to do some work on the system because the volume shrinks. And therefore the energy goes up. And then there's going to be a drop as the reaction occurs, and that's going to be as heat. So here's my work, here's my heat. If you recall, delta U is equal to Q plus W. This is what do we call that? That's called the first law of thermodynamics. First law of thermodynamics. Well, this is the internal energy. But to make a long story short, let me just tell you the answer. What else is the same is the kinetic energy is the same. Temperature and kinetic energy, temperature is just a measure of kinetic energy. If the kinetic energy is 0, the temperature is 0. And so temperature is a direct measure of kinetic energy. And so both of these have the same kinetic energy. What's different? What's different is their potential energy. And so when we do chemical reactions, we always do chemical reactions starting at one temperature and ending at the exact same temperature. This way, when we do a delta U, if we look at U initial is going to equal the potential energy initial plus the kinetic energy initial. U final is going to equal the potential energy final plus the kinetic energy final. And what we want to do is we want to do this. Because when we do thermodynamic calculations, if there's a change in kinetic energy, we use this one. If there's a change in kinetic energy, Q is equal to the amount times C times delta T. If there's a change in potential energy, then we use this one. Q is equal to the amount times delta U or delta H, depending on the conditions we do it. If you recall, delta U is for the constant volume universe. Delta H is for the constant pressure universe. Delta H and delta U are for two different scenarios here. And so it depends on what types of conditions. Do we do this in a bomb or do we do this in the open lab? If we do it in the bomb, you certainly don't want to use delta H. You got to use delta U. And so this type of stuff you need to review for thermodynamics part 2, if this isn't totally clear. Well, anyway, the kinetic energy doesn't change, just the potential energy. This blip here for this, the internal energy change is always this, and so we see how the surroundings interact, and this is where the enthalpy comes in. We're going to get work done by the surroundings. How do we know? Because of the enthalpy. You can tell those types of things. So start reviewing the. Start reviewing that because we're hitting this right away. Chapter 13, starting Thursday. Chapter 24 is some nomenclature stuff. And then we're going to finish chapter 13. The way the tests are going to work in this class is when we finish the chapter, then we'll have the test the following week. So let's say we finish it here, we'll probably have the test here. And so what I'm going to do is I'm going to break it down pretty much chapter exams rather than multi-chapter exams. So we'll finish chapter 13. Your test is going to be on chapter 13, probably this on September 14th if I stick to the schedule. Your homework for chapter 13 will be due on this day. Then we'll start, we skip chapter 14 because chapter 14 is covered in Chem 1A. We go to chapter 15, finish chapter 15 around here. We'll have the test probably on this Tuesday here. And so you'll see the syllabus has no test dates. It depends on when we finish the chapter. You can expect the test the following week. And this is going to present a problem when we get to the end of the semester. When we get to the end of the semester, we finish chapter 25 here. I'm not going to have you guys come in during the break here. When we finish chapter 25, I'm not going to have a test here. Chapter 25, we're just going to fold into the final exam. Probably chapter 24, part 2, we'll probably fold that into the final exam as well.
How many quizzes?
There will be a lot of little quizzes. The quizzes are pretty much unannounced quizzes. We'll have quizzes. In fact, we're going to have a quiz today. I'm going to announce it. We'll have a quiz today. It's only worth 1 point out of 1,000 points, so it's not too bad. Just to get things started. Maybe we'll have more than one quiz. All right, any questions on the schedule here, the syllabus? On the test, yeah, for sure on the final exam. On the other tests, I haven't determined. The other tests are not very long. And it's going to be a mix of multiple choice and free response type questions. And so maybe one of the short Scantron sheets might be. I'll let you know as we get closer to the test. Okay, anything else? All right, we're going to take a break. Today's going to be a lecture day, so we'll take a break let's go for a 15-minute break here. We'll start again at 11.